Welcome to. Good morning and welcome to the periodical seminars of the Netpore Cost Action. My name is Luca Borino. As you can see, I'm not Frederic Cunen. She's traveling today, so it's my honor to present the two speakers of today. The first is Joan Josep Carvajal from University of Rovira i Virgili, Tarragona, and the second is Gregor Sulka. We have about 30 minutes each, and so I will spend just a few words presenting the first speaker. Joan Josep Carvajal has been bachelor and PhD in chemistry from the University of Rovira i Virgili, Spain, postdoctoral Fulbright Fellow at Stony Brook University, US, and then researcher and associate professors in material science at University of Rovira i Virgili. He has a side of his activities in science activities. He has also a strong interest in the dissemination of science in general and taking care of PhD careers and training programs. So I leave you the word and the screen, please.
Thank you very much, Luca. For me, it's a pleasure to participate here. I will share my presentation, and I want to present to you today the work that we have been developing for the last more or less 8 years in the synthesis of porous gallium nitride for different applications. And basically, my presentation will be based on an introduction about why it's interesting to produce these porous materials, then presenting the particular methodology that we use to produce porous gallium nitride through a chemical vapor deposition system, how then we transform this system of growth to produce epitaxial layers, porous epitaxial layers of these materials, and finally I will present the main devices that we fabricated with these porous materials. So basically, when we talk about wide bandgap semiconductors, as it is the case of gallium nitride, porosity makes that the material exhibits unique properties, like, for instance, bandgap shift, efficient luminescence, high surface area, and size selective absorption that makes that we can use these materials in a very wide range of applications, going from advanced microelectronics, sensoring, or optoelectronics that are the ones that are of interest for us. But one of the critical points is that the development of the processing methods for controlling the optical and electrical properties of these materials really rely on the method of preparation that we are using. If we are talking about gallium nitride is a wide bandgap semiconductor that it's very important, especially for social solid state lighting. It's part of the family of 3 nitrides, and apart from being used in almost all the white LEDs that we are using nowadays, has also important applications for high power, high frequency, and high temperature applications, since as we can see here, the theoretical limit of power that we can use in gallium nitride based devices is much higher than the one that we can use, for instance, in gallium arsenide devices. When we focus on porous gallium nitride, some of the properties that we can find in this material that make it attractive for us, it's, for one side, the potential shift of the absorption band edge farther into the violet due to the quantum confinement effects. From another side, it can be used as a buffer layer or template for heteroepitaxial growth of lattice mismatch materials with low density of defects, and also in the development of sensors and detectors operating in the visible and the UV with enhanced sensitivity, and the development of LEDs, as we can see here, with increased light extraction efficiency due to the multiple reflections that light can have in the pores. Apart from that, it has also been used in the fabrication of methanol and related fuel cells, and also in the photocatalytic response for the production of hydrogen by water splitting. Normally, nanoporous gallium nitride is produced by top-down techniques like electrolytic etching, electrolysis direct and metal-assisted chemical etching, dry etching, anodization processes, etc. All of them have drawbacks. The first one, it's the lack of control of the pore morphology, but also the pore arrangement. There is also that the uniformity of the substrate will condition the porosity that we can get in the material. Most of these techniques can induce surface damage on the substrate, but also, as we can see here in those images, pores tends to coalescence with time of reaction. And some of these samples, some of these techniques require to establish an electrical contact to the sample. In 2009, we identified a new method to produce as-grown nanoporous gallium nitride particles, so using a bottom-up approach, using a very simple chemical vapor deposition technique, as I'm showing here. Basically, what we are doing is just the direct reaction between gallium and ammonia to produce this porous gallium nitride in a tubular furnace. And the critical point here is where the source of gallium and the substrate are located. In fact, we find out how to produce these materials by an accident, because we were interested in that time in the production of nanowires of gallium nitride, that normally the substrate is downstream of the reactor in the system to respect the position of the gallium source. The gallium source fall down in the system, and then we investigated what was happening, and our surprise is that we obtained these nice particles with a porosity inside of them. The operational parameters that we have to understand are the substrate temperature, the flow rate of ammonia, the pressure, the growth time, and the distance between the gallium source and the substrate. And we discovered by changing those parameters that the conditions to obtain those porous particles are very limited. Just by changing the flow of ammonia or the temperature, we can see that the morphology that we are obtaining is not exactly the same that we obtain in these precise conditions of growth. Even if we change also the pressure in the reactor, we can see that, for instance, this 15 torr is the pressure that we use. If we reduce it, we obtain like thinner plates that might have some porosity, but if we combine processes in which we are changing the pressure during the synthesis process, we can start having a core with those porous particles, but then a smooth lateral part of the particles that might be interesting, for instance, to establish the electrical contacts. If we do the opposite, for instance, if we start with 15 torr and we increase it to 150 torr, we can see that the morphology of the particles is again different. I don't know if you can see here the very small pores that we have, but if we again change the pressure during the process, what we can observe is that we modify again the morphology of the particles, and we can control even the number of pores to reduce it to just one on the particles. If we analyze the morphological and structural characteristics of our samples, we can see that the morphology is consistent with bursite hexagonal gallium nitride, and by high resolution TM we can see that the space between the atom planes that we obtain are confirmed that we have the bursite structure, and even by the electron diffraction patterns we can observe that the pores that would be perpendicular to those faces that we have here are parallel to the z-axis direction. In fact, to characterize more in depth the pores, what we used, I will try to activate this video, is that we use focused ion beam time resolved tomography. So we are slicing little by little those particles, and we are observing how the pores are appearing. And here I extracted some pictures of these videos in which we can see where the pores are located. In fact, if we analyze more in depth, we can see, for instance, here, this part in pink are the internal view of the pores. And if we analyze their structure, we can see that they are independent one from the others, and then they do not cross among them. Up to this point, we were working with boron nitride substrates, but then we wanted to move to more useful substrates, that is silicon. And we could observe that by reducing the temperature of growth, we could get similar structures than the ones that we obtained in boron nitride. So just changing the temperature allowed us to do this step. In that case, we needed to introduce a metallic catalyst in the system to favorize the nucleation of the gallium nitride particles. We investigated gold and platinum, and we observed different things that are interesting. From one side, that we are generating layers, polycrystalline layers, obviously, but in which we have the intraparticle porosity and the interparticle porosity that can be useful for different aspects. But when we characterize them by X-ray diffraction, apart from gallium nitride that was expected and silicon nitride, because it's the nitridation of the substrate that we are using, we also observed the formation of an alloy between gallium and gold, or gallium and platinum. And when we analyzed the location of this alloy, we observed that it was here, we peel off the porous layer that we had. This gallium gold alloy was located in between the substrate and the porous layer, and this allowed us to determine that the mechanism of growth was by vapor solid mechanism. Another advantage of using this metallic catalyst is that we can use it as an electrode, okay, to characterize electrically the samples. And what we observed is that we had a near-ohmic weak Schottky barrier formed by high work function metal as platinum and gold. And in fact, it's this intermetallic gallium gold or platinum alloy that lower the Schottky barriers. And we could confirm that this gallium nitride as produced is N-type with a net impurity concentration of the order of 1.6 to the 10 to the 16 charge carriers per cubic centimeter, with mobilities around 208 centimeters to the square, volts to the -1, second to the -1. If we analyze the luminescence properties of these materials, we can see that we have only the single peak generated by the band edge of gallium nitride. And here with the cathodoluminescence images, what we are observing is that those are the optical image. This is the SEM image. We can see that the destruction of light is more efficient in the areas surrounding the pores. This was okay, but for practical applications, we needed to produce epitaxial layers of this material. For that, we investigated the use of different substrates like sapphire, silicon carbide, aluminum nitride, and the same gallium nitride. They have different lattice mismatches with gallium nitride, and depending on that, we will see that we can obtain those epitaxial layers or not. In fact, with sapphire, although at low magnification, we can see a good coverage of the substrate. When we magnify the image, we can see still that we have this microcrystalline structure that it's not what we were looking for. When we move to silicon carbide, in which we reduce the lattice mismatch, we started to see that the particles tend to align, but still we can see the limits between the different particles. If we reduce even more the lattice mismatch, we go to aluminum nitride. We observe this structure that at the beginning we did not understand, but as I will explain in a second, finally we could understand what was happening here. And finally, we move to gallium nitride, in which we don't have any lattice mismatch with the structure, and then we obtain these nice porous epitaxial layers in which we cannot see the borders between the different particles, so it seems that it's a continuous layer. So the lattice mismatch between gallium nitride and the substrate plays a big role on getting the continuous porous layer that we want. And we had still to solve this thing that was happening with aluminum nitride. And what we observe is with using gallium nitride, but increasing the time of growth, we observe a similar structure. So in principle, what is happening here in aluminum nitride is to get those nice porous structures, we have to reduce the time of growth. Also, depending on the time of growth, we have a different degree of porosity and a different thickness on the porous layer that we have. And we could also even determine which is the diameters of the pores, and are in the range between 200 and 300 nanometers. Characterizing them from a structural point of view, what we observe here, we have the rocking curves of the non-porous substrate and the porous epitaxial layer, and we observe that there is a reduction in the strain of the porous layer of 0.21% that, as we will see in a second, has also implications on the electrical and the optical properties of these materials. In fact, here we have the emission generated by these porous epitaxial layers as a function of the time of growth, and we can see that as the deposition time increases, the thickness of the films increases, and the position of the nearby edge peak also increases, as well as its intensity. And what we observe is that as we increase the time of growth, there is a relaxation of the epitaxial layer that we are obtaining, so it has implications on the emission of those epitaxial layers. Also, this was confirmed by quasi-resonant Raman scattering, just by analyzing the full width at half maximum of the A1 band, and also comparing the intensity of the A1 and the first overtone of this band, the rate of intensities between these two bands. And what we observe is that, for instance, when we analyze the intensity ratio, this decreases as the deposition time increases, what confirms that we have an improvement on the crystallinity and the structural quality of the epitaxial layers that we are producing. We also investigated how it is the reflection, the reflectivity of these layers, and as expected, since we have porosity induced, there is a significant reduction of the reflectivity, especially in the visible part of the emission spectra, which can be important for sensing applications using light. And we also observe that there is a correspondence between the position of the pores and the brightest emission spots that we are observing in our samples. By AFM, we could also determine not only the size of the pores, but also the walls between the pores, because as we will see in a second, this has very important implications in quantum confinement response that we are getting in our material. And we can see that as the deposition time increases, both the pore diameter and the wall thicknesses between pores increases with time. We also analyze the wettability of those surfaces, since porosity might induce hydrophobicity, and in fact, this is what we observe. We are moving from the hydrophilic regime for the samples growth at lower times to the hydrophobic regime for the samples grow at longer times. So we can modulate the hydrophobicity depending on the time of growth and obviously the porosity of the sample. And the reason for that is that the wetting mechanism that we have is based on the Casey-Baxter model, in which we have a balance between the capillary force and the pressure of trapped air in the pores. So when we have air trapped inside of the pores, the microstructure will produce a more hydrophobic surface. Finally, going to the last part of my presentation, I wanted to present the main devices that we fabricated with these structures. Here, for instance, I'm presenting a partial porous p-n junction. So we have a non-porous p-type gallium nitride substrate. On the top of it, we are growing an n-type porous gallium nitride layer. Here we can see the difference between luminescence and the spectra that we are obtaining for the substrate and the porous layer, and we can see that this is brighter in the porous layer. So we have a more uniform distribution of luminescence in the porous layer, and the pores do not quench this luminescence, apart that the light extraction is more efficient in the porous layer. If we go to the electrical characterization, we can see this nice curve indicating that we have a diode behavior with a turn-on voltage between 0.5 and 0.68 volts. This is the first confirmation that those structures behave more like one-dimensional structures than continuous continuous layers. We also observe that by EDIC measurements, there is the pores do not act as traps, so we can work with them without any problem. The following step was, okay, can we produce P-type gallium nitride, porous gallium nitride, with our system? And just by introducing a magnesium precursor, in that case it was magnesium nitride, we could generate, as we can see here, the emission, the typical emission of the donor-accepted pairs when we are doping with magnesium, typical of gallium nitride, so indicating that we are obtaining porous P-type gallium nitride. And in fact, when we are growing these porous P-type layers on the top of a non-porous N-type substrate, again, we observe this nice diode curve. Here, even the turn-on voltage is reduced, and it's similar to the one that we can observe in indium nitride or gallium nitride nanowires. There is also a linear tendency up to 5 volts, similar to the one that we can get in non-porous gallium nitride diodes, and we could estimate that the Hall density in those structures was of the order of 9 per 10 to the 18 per cubic centimeter. Then the following step was, okay, can we produce fully porous PN junctions just by growing sequentially first a porous N-type gallium nitride, and on the top of it a porous P gallium nitride layer? The response is yes. Here we have the images of the both layers, the structural characterization that indicates that there is similar relaxation for the two layers. And when we are analyzing by cathodoluminescence and by photoluminescence the emission properties of those materials, we can see clearly the undoped porous gallium nitride, that is black because the number of charge carriers that we have in this layer is quite low, but we can distinguish it from the P-type porous gallium nitride layer, and we can also observe the differences in photoluminescence between these two layers. And the electrical characterization indicates again that we have a nice diode response, and the most interesting thing is that the current that we obtain at a fixed forward voltage is 3 orders of magnitudes higher than the one that we obtain in the partial porous PN junction. So this is good. Here is the homogeneity in one of those devices and the reproducibility among 25 different devices. So we can see that they are quite nice. We also characterize what is happening when we are increasing the temperature, and what we observe is that as the temperature increases, the GNI voltage decreases, but there is no breakdown observed even at operating at 10 volts and a temperature of 673 Kelvin. We also characterize those PN junction as electrical rectifiers. Here we have the curves for the porous, the partial porous layers, and here for the fully porous electrical rectifiers. And what we can see is that except for the smallest voltage applied, in which there is no clear rectification, for the rest of voltages that we applied, we can see this rectifying behavior up to a value of 5 volts, in which we observe a high leakage voltage, and it has the lowest rectification ratio. But in general, what we can see here is that we have very stable values of current with time at both forward and reverse bias. So we have a stable rectification. And finally, talking about the LEDs that we can develop with them. Here we have a partial porous LED fabricated with porous N-type gallium nitride. Here we can see the emission. We have a turn-on voltage of 7.5 volts, a breakdown voltage of 25 volts, and we can see here that the emission of this LED shifts toward higher energies as the voltage increases. Then to improve, this is what we are doing nowadays, to improve the performance of these LEDs, we need to increase the number of charge carriers that we have in the N-type porous layers. For that, we are trying to dope with silicon. Here is the results that we are obtaining. And here, what you can see is that when we have this porous silicon doped N-type gallium nitride grown on a non-porous substrate, here is the emission that we are obtaining. The turn-on voltage is reduced to 5 volts. We have an operation up to at least 40 volts. We did not pass this voltage, and the band is much more complex. That gives us this white color that we are observing here. And as a curiosity, just to finish, when we are doping with magnesium nitride, if we use a low quantity of magnesium nitride, we are doping the structures with magnesium. But if we are using higher concentrations of magnesium, we obtain this layered structure, in which here we have the substrate. Here we have this alloy between gallium, the catalyst that we are using, and magnesium. Here we are observing the appearance of magnesium oxide, and here the doped gallium nitride. So at the end, what we are having is we are forming a metal oxide semiconductor diode with a high dielectric constant insulator, that is magnesium nitride. And we believe that this can be used in the whole family of 3N materials, especially for capacitive biosensing. And with this, I arrived to the conclusions of my presentation, in which we demonstrated the fabrication of these partial and fully porous PN junctions with excellent junction characteristics and with potential applications in the development of encapsulated gallium nitride-based LEDs. Also, that this porous PN junction can be grown by sequential chemical vapor deposition over large areas. And we believe that this investigation can be extended to other members of the 3-nitride family for different applications. And finally, that this high surface area diode made by this route do not require complicated core shell structures in nanostructural arrays, and may be viable routes to chemical stable wide bandgap biosensors. I would like to finish thanking my collaborators, the 3 doctors now that helped me during that time, that they were PhD students with me, Dr. Alexander Bilusov, now at University of Uppsala, Dr. Josue Mena, now at Umeå University in Sweden, and Dr. Jordi Aixart, that now is at CCT, that is a company here in Spain. Also, Professor Colm Dwyer and Professor Peter Parbrook from the University College Cork in Ireland, and Dr. Vitalis Subialevich, also from the Tyndall National Institute in Ireland, and Professor Juan Jimenez and Dr. Oscar Martinez from the Universidad de Valladolid here in Spain. And thank you, you all, for your attention.
Thank you, Joan Joseph. You stayed perfectly in the time. So we have 5 minutes for the questions.
Good morning. I have a question.
Yes.
Can you hear me?
Yes, we can.
Okay, good morning. Thank you for your presentation. I was wondering if you could comment on the cathodoluminescence maps that you showed in one slide, the one for the fabrication of partially porous PN junction. So you have the cathodoluminescence for the non-porous gallium nitride and the porous gallium nitride. I was wondering what is the difference that you observed concerning maybe the intensity of the luminescence as well as the distribution.
Okay.
Thank you.
let me share again my presentation, and I'm going to this slide in which we can see this. And here, for instance, this is a cathodoluminescence image in which we can see the difference between the non-porous substrate and the porous layer. This was done just recording the image at the interface between these two layers. So I would say more or less in this area here. Okay, so then we can see the two layers. One might think that the height of the different layers is different, so it might have an impact also on the image, but the thickness is so low that has really no significance in that case. But from other side, when you record the spectra in the two regions, you can see that it's totally different. This is the typical one for the N-type gallium nitride, and this is the typical one for this is the typical one for the substrate. I was wrong. This is for the porous layer, and we have only the band edge emission that is typical for N-type gallium nitride. And here, this is the one for the substrate that, since we have this donor acceptor pair band, this is typical from the P-type doped gallium nitride. I don't know if this answers your question.
Thank you. Yes, thank you very much.
Okay, no problem.
Any more questions?
It seems that we can move to the following.
Yeah, if not, we thank the speaker again, and we move to the talk of Gregor Sulka. Just a few information about him. He received the PhD in chemistry at the Jagiellonian University in Krakow, Poland, and he has experience in the Catholic University of Leuven, and also at the Max Planck Institute of Microstructural Physics, Halle in Germany, and is currently full professor and head of the electrochemistry group at the Jagiellonian University in Krakow. So please.
Thank you, Luca, for a kind introduction. I will share my presentation. Okay, let's start. Can you see it?
Sure. It's not in.
Okay.
Full screen. Okay, perfect.
Yeah. Okay. Let's start. I would like to say a few words about nanostructured anodic metal oxide, about the synthesis and application such oxides. So we are based in Krakow. Jagiellonian University is a quite large university, educates about 40,000 students at 150 different fields of studies, and Faculty of Chemistry is not so big. We've got 12 departments. Faculty employs over 180 academic teachers, and we teach about 1,300 students at all levels of studies. So faculty is located in the relatively new building. As you can see, there are some pictures here. Electrochemistry group is not so large, but we are interested in some materials synthesized by electrochemical way, and they use for different applications. First of all, we synthesize nanoporous nanostructures or different nanostructures of metal oxides, and use them for electrochemical sensing of different compounds, also for biomedical applications. And most important, I think, we are synthesizing materials for energy conversion and storage and photoelectrochemical water splitting applications. Also, some part is devoted to bioelectrochemical systems. When we are thinking about anodic oxidation of metals and the formation of nanoporous metal oxides in this way, we can anodize, of course, metals and semiconductors, but the most widespread technique is anodization of aluminum, as you know probably, but other metals can be also anodized. I would like to say a few words about that, which are highlighted in green one. What is anodic oxidation? It's a simple electrolysis. And the metal which we want to anodize and transform his surface into porous or tubular metal oxide, we treated such a metal as an anode. The process is quite simple. During the process, the surface of a metal is oxidized and the ion are released. Of a metal ion are released at the anode. At the cathode, generation of oxygen-bearing ions occurs, and the overall reaction is a reaction between both of the products and the formation of oxide layer. Of course, in the anode, the side reaction can also occur, and the main reaction which can be present except that oxidation of metal is generation of oxide, of course. The method is quite simple and is cheap. The method doesn't need any advanced equipment. We can anodize large samples, and we can also control morphology of from anodic layer. The morphology could be different. Compact layer can be formed, or the porous layer, like in that case, disorder porous layer can be also formed, and also nanotubes, nanofibers, nanorods, nanowires can be formed also by anodic oxidation of metals. When it comes to anodization of aluminum, which is known from almost 100 years, that two different approaches to do that. The first one is based on the using a substrate which was previously pre-patterned by using a mold, for instance, and such a pattern on the substrate acts as nucleation sites for a generation of pores during anodization. The second approach, much cheaper, because the mold should be prepared by lithography techniques. The second approach is based on the self-organized anodization of aluminum, and it consists from two steps. First anodization results in a disordered porous structure, and we can remove this oxide from the substrate, and we observed some concaves on the surface of aluminum, and this concave acts as pattern for generation of oxide in the next step. Using both approaches, we can observe in case of pre-pattern anodization, we can observe different arrangement of pores, like hexagonal arrangement of circular pores, square pores, triangle pores, checkerboard-like pores, and triangle circles and triangle diamonds also can be formed using that pre-pattern substrate. In the case of self-organized anodization, always we observe hexagonal arrangement of pores, but we can injure a little bit a shape of a channel. For instance, we can prepare conical pores at the cross section, step shape or step shape reversed, wide branch, multi-level branch, serrated like that one, or with modulated pore diameter like here or here, or ratchet tip asymmetric like that. In that case, it's enough to apply to different voltage during anodization or different current. But of course, it's not very easy, but it's possible. And here are some samples of anodic aluminum oxide prepared in different electrolytes. As you can see, there is a different diameter of pores and also different spaces between the pores, because different anodizing potential were used for that. The channel are straight and perpendicular to the surface. But using advanced technique of anodization, like pulse anodization, we can prepare also the templates or oxide layers with modulated pore diameter. Here is the example of such a layer when the pores has a diameter 35 and 60 nanometers. The alternating layer formed by using alternating high and low voltage pulses. The second example, it's a fabrication of wide branch pores, and so we have to reduce the voltage applied during anodization, but the reduction should be appropriately chosen to obtain wide branch pores like in that direction, or 2 levels wide branch pores like that. The number of branches can be determined from that equation. Further examples, we prepared just by exchanging of electrolyte during anodization, like step-shaped reserved or step-shaped channels, or with modulated pore diameter, but in that case we change the electrolyte during anodization, or serrated channels like in that case. And some examples of applications. Nanoporous anodic aluminum oxide. It's quite easy to sputter on the top of such oxide gold layer or other metal thin layers. Here's here's an example of a gold thin layer which was sputtered on the top of such a substrate, and the thickness of that layer was something like 150 nanometers. And we use such a material as an electrode for electrochemical sensing of adrenaline, and we, as you can see, we were successful, and that sensor was able to determine adrenaline in the presence of uric acid, and we verify this application by analysis of real sample. It was the injection ampoule of adrenaline. The second example is the using that nanoporous layer as a type of valves which are capable to release loaded compounds on the demand. We grafted on the surface the pore diameter in that aluminum oxide was something like 30 nanometers. We grafted polymer PNIPAM brushes on the top of that surface, and when we increase the temperature above the lower critical solution temperature for these polymer brushes, they shrinks and open the pores. We can load some compounds. For instance, in that case it was calcine, and then we can lower once again the temperature below lower critical solution temperature, and that nanowires brush is spread out and close the mouth of the pores, and then we can on the demand release them from that containers. So there are some proof of that experiment. And another example is making a Bragg reflector. We used anodic aluminum oxide with modulated pore diameter, like in that case. After a lot of steps, as you can see here, we just obtain 50 pairs of alternating layers which differ in the porosities. So when the difference in porosity was obtained, we use the light to irradiate these samples, and we observe reflection of that alternating layers of the reflector and the Bragg mirror into ranges of wavelengths. The red curves is a measured one, the blue one is a calculated theoretically. So you can see that it's a quite good coincidence both of curves. Here is an example of preparation of nanoporous oxide layer with conical shapes of channels and using them for a generation of nanocon array electrode. We just use anodization and chemical etching alternating processes to form template with conical shape of channels, and then we spotted copper and deposited copper, and we obtained nanocones, copper nanocones with a diameter of about 90 nanometers and height 150. Top views, side view you can see here, and we use it as an electrochemical sensor for sensing of hydrogen peroxide, and there are some examples of that. And the most widespread application of anodic aluminum oxide is a template for the generation of nanowire arrays or nanowires, different types. There are a few steps to do that. We have to remove aluminum substrate from the bottom, and then we have to open the pores, and then we have to sputter the conducting layer, and then perform electrodeposition and remove the template. And finally, we can achieve a nanowire array, and we produce different nanowires. Here are some examples of silver nanowire with different diameters ranging from 550 to 300 nanometers, and with various materials like silver, gold, copper, tin, antimonium, polypyrrole, and so on. There are further examples like alloy nanowires, gold, silver, multi-layered nanowires. The segments are quite easily visible. Gold segment, of course, and wide branch gold nanowires. Here's example of polystyrene multi-branch nanowires, and also nanowires with modulated pore diameter. There are nanowires made of nickel and silver. And here are some examples of using prepared nanowires for electroreduction of chloroform. We used silver nanowires and also silver nanocones, and we compared them, and it was found that best performance it was for silver nanowires, probably due to the higher surface of the nanowires of the electrode. And quite interesting that quite interesting fact it was that we observed the shift of reduction potential of chloroform towards less negative less negative potential, so it's quite beneficial fact. And example of preparation of composite nanowires. We prepare composite nanowires which consist of silver nanoparticles which were spread inside the polypyrrole nanowires, and we use them. Of course, we studied annealing process also, and we observed some segregation, aggregation of nanoparticles, and both types of nanowires we just studied as an electrochemical sensor for hydrogen peroxide. Even after storage time, 10 days of storage, the performance was quite okay. Another example of composite nanowires made of nickel hydroxide nanoparticles dispersed into polypyrrole nanowires, and we used that composite nanowires as material electrodes for supercapacitors and studied the properties of such arrays. Another example, here we've got multi-layered nanowires, multi-layered made of platinum and platinum cobalt layers, and we studied magnetic properties of such nanowires. And the last one example of a material which was prepared based on the anodic aluminum oxide is semiconducting nanowires obtained by electrodeposition, mainly indium antimonide nanowires. And we studied properties of the array, but we also studied conductivity of a single nanowires before and after annealing, and we observed quite interesting behavior of changing type of conductivity after annealing. Let's switch to another oxide. Now I will talk about titanium oxide, made also by anodic oxidation of titanium. But in that case, we are not using water-based electrolyte, but we have to use ethylene glycol or glycerol with addition of fluoride ion and water. As you can see, we can produce quite well-arranged nanoporous oxides on the top of titanium. There is a top view, bottom view, and cross-sectional view. We typically use three-step process, free anodizing process. So after each anodizing, we remove oxide layer in order to observe quite regular arrangement of pores. Of course, we can also a bit engineer tune the pore diameter, changing potential during anodization in the certain range. Also the cell size, I mean that the size of that cells can be a little bit tuned by potential applied during anodization. As prepared, anodic titanium oxide is amorphous and is not quite okay for different applications. So we studied annealing process at different temperatures after anodization. As you can see, below 700 centigrade, the porous structure is still preserved. We observed also generation of rutile grains at the metal oxide interface, as you can see, and then the rutile grow up with a temperature. But the best rutile content was observed in terms of electrocatalytic application, was observed for samples which were annealed at 400 and 500 centigrade. There is example of using such a anodic titanium layer on the titanium as drug delivery system for bio applications. We load into that nanopores two drugs like ibuprofen, anti-inflammatory drug, and also gentamicin, antibiotic. And we studied the kinetics of release after loading, and we observed two stages of delivery of the drug. First stage, it was desorption from the surface of oxide layer, and the second one is a combination of desorption and diffusion from the pores. And we just propose the model called DDD model, desorption, diffusion model. For the drug, we also calculate that kinetics for different structures of titanium oxide, like amorphous anatase or mixed anatase rutile phases of that oxide. Further, we use that titanium oxide as potential materials for implants, and we studied inhibition zone for gentamicin loaded titanium oxide, and we also studied cell culture. Here are some examples of osteoblasts like cell line MG63, and also we studied the cell line SAOS2, and we studied cytotoxicity of the surface adhesion of cells, cell morphology, and proliferation of cells on such surfaces. That work is still quite at the beginning of developing in our research group. Now I would like to switch to another applications not related with bio. It's a generation of green energy. As you know, the consumption energy rises from decades, and the percentage of renewable energies also rises in the group of energy sources. And one of the system which can be used for generation of green energy is a photoelectrochemical cells. It's a photoelectrochemical cell. A typical photoelectrochemical cell consists of the photoanode, or photocathode also, it could be, but in our case it's photoanode, made of semiconductor, and the cathode. During the irradiation with a light on the photoanode, generation of holes and electrons, separation of holes and electrons occurs, and the electrons can be used for generation of photocurrent, and that it can be used for generation of hydrogen and the cathode. So the semiconductors which should be present on the surface of the photoanode are from the group of that one. Of course, there are not all of them, but it could be titanium oxide, it could be zinc oxide, also tungsten oxide. And we used our anodic oxide for water splitting application in such cells. And you can see that this anodic titanium oxide used for generation of photocurrent. Titanium oxide was formed at different anodizing potential, ranging from 300 to 30 to 70 volts. And as you can see, the generated photocurrent is present as a function of polarization potential used for applied to the electrode, and also wavelength which irradiate the surface of a semiconductor. The maximum of generated photocurrent was observed about 340-50 nanometers, and we also calculate quantum efficiency of conversion of photon into electricity, and we observe the best results for a sample which were formed at 40 volts. We check also the temperature, which was best one for generating of anodic titanium oxide, and the best temperature was close to the room temperature. It was 20 centigrade. It depends. The best current efficiency, sorry, not current efficiency, but efficiency of transformation photo into electricity was the best one at 20 centigrade, and is related directly with the thickness of the oxide which is formed at that temperature. We studied, as I told you before, we studied also annealing process, and here are some examples of photocurrent density generated at three different samples, at samples which were annealed at different temperature, and the best results was observed for samples which were annealed at 400 centigrade, and also quantum efficiency was best one for that sample. We also estimate the band gaps of that materials. We studied some semiconducting properties of such materials, like donor density, like flat bud potential was also estimated, and so on. And we decided also to use anodic titanium as a photocatalyst for decolorization of metal red. Metal red is just a compound which absorbs at the band. Absorption band is quite large at 520 nanometers, and we irradiated the solution in the presence of catalysts, and we observed diminutions of the intensity of the band, as you can see. After 6 hours of irradiation, after 9 hours of irradiation, we observed more than 80% of degradation of the dye. The kinetics of degradation is first order as typically, and that benefit of using such a catalyst is that it can be used several times without a complicated procedure of regeneration of catalyst, and because no filtration is needed. In that case, we just put the catalyst into the solution and take it out immediately after finish of a process. We can also boost photoelectrochemical properties of our oxide by using, by engineering the internal structure of the oxide, like in that case, making different structure of channels. We can use three-dimensional structure, and we can deposit metallic nanoparticles, which are which acts as a traps for electrons during the photoelectrochemical water splitting. And here's an example of the using of the different types of materials with dispersed nanoparticles on the titanium oxide. We used copper, silver, and gold nanoparticles dispersed on the surface. We observed the best photoelectrochemical properties for in terms of best quantum efficiency for gold nanoparticles dispersed of for materials with gold nanoparticles dispersed on the surface, and also we studied photocatalytic properties of such materials, also observing the best degradation of metal red in case of gold nanoparticles dispersed on the surface. Another approach was based on the changing the structure of a channel. As you can see, the tubes, channels, titanium tubes are now consist of some rings on the surface and smooth parts, and we can also change the thickness of the ring, thickness of the smooth parts, and so on. And we studied photoelectrochemical properties, and it was observed that for that samples was the best results in terms of quantum efficiency of photon conversion. And the third approach to boost some photoelectrochemical properties was using the three-dimensional substrate for that, and we studied titanium mesh as a substrate, and also a plate, titanium plate, and red curve is for mesh, blue one is for foil. And as you can see, the quantum efficiency was also the best one for three-dimensional substrate. Band gap was similar for both substrates. Let's switch to another oxide. Is tungsten oxide. Now is anodizing is performed in the water-based electrolyte, but the difference is that we cannot observe order structure in that case. We studied also annealing process, and it was interesting that during annealing, the thermal oxide below the porous oxide layer is formed during annealing, and the thickness could be much higher, much longer, much higher than for porous oxide, even at the low temperature of annealing, like 500 centigrades. Of course, we studied also photoelectrochemical properties. Maximum of generated photocurrent, it was at 350 nanometers. It's UV range, and the band gap also we determined it's about more than 2.8 electronvolts, and the quantum efficiency was the best one for a sample which was annealed at 500 centigrades due to the presence of a thermal oxide at the bottom of porous oxide. We tried to, since the tungsten oxide, similar to the titanium oxide, absorb the mainly UV light, we tried to synthesize them by two approaches. Synthesize to visible light, of course. We used wet impregnation in transition metal oxide, and we try to electrode deposit another semiconductor on the top of them, which has not so broad band gap. In both cases, we were successful, and we observed enhanced quantum efficiency of photon conversion in visible light region, as you can see on that pictures. And the next oxide which can be produced by anodization is tin oxide. In that case, we can use acidic electrolyte and alkaline electrolyte, but using acidic electrolyte, we have to be careful. On the top, we observe, of course, porous structure, but at the cross section, we observe just stacked oxide layer, as a lot of layers which are stacked one on another because of oxygen blocking effect occurring during anodization. Oxygen is generating and causes the detachment of continuous detachment of oxide layer during anodic process. So we switch to another electrolyte like sodium hydroxide, and we observed here we use pulse anodization process, and we observed quite continuous layer, but with modulated channel diameters, with higher diameters and lower diameters, consequently to the anodizing potential used during anodic process. We studied also for tin oxide photoelectrochemical properties. We use it for water splitting application. We also determine band gaps of such semiconductors and so on. And we produced also by anodic oxidation of tin, but not porous oxide, but nanowires. We started anodization of zinc in that process using electrolyte based on the sodium bicarbonate. And in that case, the mechanism is completely different. And we observed formation of nanowires made of zinc hydroxide and zinc carbonate. And after annealing, that nanowires are transformed into zinc oxide. We also studied some optical properties of such layers and so on. Finally, we also were successful in generation of nanoporous zinc oxide by changing the conditions. And we observed some spongy-like morphology of oxide with continuous more or less continuous layer. We studied a lot of properties of the oxide layer because it's still the question, what is responsible for, which effect is responsible for a dark color of that oxide. We observed high amount of oxygen vacancies and zinc interstitials atoms in that structure. Probably the dark color is a result of existence of some additional electronic states in the bandgap or effect of nanotopography of zinc substrate. Especially the dark color is visible for that samples which are anodized at 4 volts. Even after annealing, the samples has a dark color. The second, the next last of the next example is zirconium oxide. We studied 2 different substrates, but as you can see, there is no big difference in the anodized layer. So the oxide has a similar pore diameter, and we use such structures as surface enhanced Raman spectroscopy substrates, and also photocatalyst for the colorization of metal red. Interesting thing that during anodic oxidation of after the anodic oxidation of zirconium, zirconium oxide is already crystalline, is different from other anodic oxide, as we noticed for the first time this fact. And the final example is anodization of iron. We also perform in ethylene glycol electrolyte. As you can see, we studied different temperatures of anodization, different voltages, annealing process, and also photoelectrochemical properties of such layers. Okay, to conclude, anodic oxidation is just simple approach used for obtaining nanoporous nanotubular metal oxide. Morphology of oxide layer can be tuned a little bit by anodizing conditions, by choosing appropriate conditions, and also morphology affects the semiconducting and photoelectrochemical properties of received materials. And finally, nanoporous anodic metal oxide can be used for different various applications, as I tried to show you. Finally, I would like to acknowledge the people who I work with. There are some academic teacher, PhD students, and students who work in our group, and financial support from different agencies, as you can see here. And thank you very much.
I have a question. It's very interesting, the templating of the different materials, nanowire with the aluminum oxide structures. So it's very interesting to have different metals, nanowires, but I saw that essentially you are dissolving the template in liquid.
Yeah. Yeah.
Which is the solution you are using? An alkaline.
Okay, yeah. There are two approaches you can use because aluminum oxide is can be dissolved in phosphoric acid, and the second solution, it could be sodium hydroxide. So you have to be careful what the material is inside, because you can damage the material during the dissolution process of a template. Yeah, and there is no way to remove the anodic alumina with dry techniques. No, but you can use different templates, like polymeric templates, like polycarbonate templates. So you can dissolve the template after deposition of nanowires in organic solvents. Yeah, because essentially you're dealing with drying, and all the pictures you showed are in some way affected by the drying of the structures. So you can have some stitching, or you have a strong deformation of the structure. So I was guessing if there are some limits, of course. Yeah. Okay, thank you very much. Thank you. Other questions? If not, so we thanks the speaker again. Thank you very much. And thank you. And we'll meet with the next scheduled seminars from the Netpore cost action. Thank you very much, and have a nice day. Thank you very much. Bye bye. Bye bye.